let us start. So today we will be studying gravitational wave, and to study the gravitational wave, the first assumption that we will make is let the gravitational field is weak. So this can be thought of a case when we are very far away from the source and the gravitational radiation that is emitted by the source uh, reaches us and it is a weak field. Okay, therefore any perturbation it creates into us is very weak. So what we can do is then with this assumption is that we can decompose the general curve. That means the curvature is minimal at the point. Okay, the curvature at the point in which we are into a flat Minkowski metric, which is can be thought of a background, and over it a small perturbation. Okay, so this is the actual uh, gravitational wave curvature, G mu gravitational curvature, which can be thought of this background, which is the Minkowski metric, plus a small perturbation H mu nu, where H mu nu is very less than 1. So when we assume that it already and tells us that we will only deal with the first order or linear in H mu nu. Any higher order terms in H mu nu, that means square or other higher order terms, should be neglected. Okay, and eta mu nu is, is the diagonal of this form. That is, we dealing in this form -1 plus plus plus, and this is the thing that I've discussed. Okay, so the theory is Lorentz invariant under this type of transformation. Once we have assumed that this H to be very small, then the theory is Lorentz invariant under this type of transformation. And so the metric eta mu nu is invariant, which makes the metric eta mu nu or the flat metric Minkowski metric to be invariant. However, the perturbation transforms as H mu nu H mu dash nu dash equal to lambda mu dash lambda nu dash H mu nu. So this is how a tensor should transform. And if I assume this to be small, then I can easily show that this G mu nu up in the this inverse of this G mu nu is nothing but eta mu nu minus of H mu nu. So this is very easy to show, and I ask you to people to do that. So let us now proceed. Once we have defined this upper G mu nu and lower G mu nu, then we can easily calculate the Christopher symbols, this gammas, and which is given by this formula. Okay. However, if I now put this form, okay, in this G mu nu and for this G mu nu, the +1, and this upper is the minus of H mu nu, then I can easily neglecting all the higher order terms in H mu nu, I can easily show that this is nothing but half of eta rho lambda total bracket del mu H nu lambda plus del nu H lambda mu minus del lambda H mu nu. So this we can find out. So this we have found out the linearized version of these Christopher symbols. Okay. Now the linearized version of this Riemann tensor can also be calculated, and you can easily show that all the other terms will go away, and this will reduce to nothing but eta mu lambda gamma of lambda nu rho minus eta of mu lambda del rho of gamma of lambda nu rho. Okay, this you can easily show. This is also very straightforward. So what we are here notice that this can be reduced in this form, because again we are neglected all the higher order contribution of H mu nu. So in the connection coefficient of our first order quantities, the only contribution Riemann tensor could be from means this linear in gammas. Even linear in gammas will only contribute to this Riemann tensor. So once Riemann tensor is calculated, so you can also do this, expand this gamma in terms of H mu nu, and you will get eta mu nu and H mu nu, and you will get this term. Okay, this is also very straightforward. You can just do a straightforward calculation and find out. So once Riemann curvature Riemann tensor is found, then we know how to find the Ricci tensor. It is just means compressing the two indices, alpha and, let us say, alpha and beta. So we will have uh, so in this we just multiply with, let us say, that rho sigma. Okay, and if I compress that, this will now this Ricci scalar tensor will be of this form. Okay, see, double derivative everywhere we have a double derivative with h mu nu or h rho mu. Okay, and if we define a stress, the stress of this part we can this stress of this perturbation as h, which is nothing but eta mu nu h of mu nu equal to h mu mu, which is this diagonal form. Then we have then and the Dilamarchian, this delta is nothing but minus del t square plus del x square plus del y square plus del z square. Okay, then I can write this in a more elegant way, and we don't need to do that. What we do is we need to calculate the Ricci scalar. Okay, because to you remember that because to find out this Einstein tensor, we need both the Ricci tensor and the Ricci scalar. So Ricci scalar is nothing but this, and this in terms of h mu nu and this Dilamarchian, it can be written in this form: del nu of h mu nu minus of Dilamarchian of h, where h is defined as this. Okay, so this then putting each and each component, every component which is tensor and which is scalar, we find the Einstein tensor G mu nu. Okay, so in G mu nu we only take means this only means here usually you will find that it is G mu nu, but here it is eta mu nu, because we are dealing with linear in h mu nu. So if there is a contribution from h mu nu from here and h mu nu from here, we will only account the linear in h mu nu term. So this h mu nu term here will disappear. Okay, so is neglected, not disappear, is neglected. Okay, so and then if I do that, I can easily write this G mu nu, the in terms of double derivative of h mu nu, the Dilamarchian, and this is the general form. So this till now it is very straightforward. Once we assume the higher perturbation of h mu nu disappear, we can write this G mu nu in the linearized form. Okay, and the linearized field equation can then be written in terms of G mu nu equal to 8 pi T mu nu, where T mu nu calculated at the zeroth order of G mu nu of h mu nu. Why? This is because for the weak field limit, the T mu nu itself has to be small, so that there are no higher order connection even from h mu nu. So the zeroth order of h mu nu, because h mu nu doesn't contribute to T mu nu, because we are dealing with the linearized version of the thing. So if T mu nu has this h mu nu term, then it can produce higher order even in the geometric part. So we will not do that. Okay, so we are assuming that even T mu nu, because T mu nu has to be small, it is of the zeroth order of h mu nu. There is no perturbation at least there is no perturbation in the energy momentum tensor. The energy momentum tensor is only due to the plane, let us say Minkowski form. Okay, so if we consider this vacuum solution, then again we don't need to consider anything that we have told about T mu nu. Is we only have this vacuum solution is to be R mu nu to be equal to 0. Okay, and we are now this equation can be easily solved, but once we get rid of, or once we understood what is the gauge invariance of this thing, of this perturbation technique that we have talked about. So where this gauge invariance things crops up. Okay, so this gauge invariance arises because we demand that G mu nu equal to eta mu nu plus h mu nu. However, this choice of h mu nu is not unique. There may be other coordinate system where G mu nu can be written in terms of eta mu nu plus some other small perturbations, but it need not to be this h mu nu, this particular h mu nu. It can be of other small perturbation. Okay, so this can be understand that in GR the coordinate transformation plays a role of Gauge transformation in electromagnetic theory. You remember that in electromagnetic theory we have this mu, this vector, okay, and we can add any del mu lambda, which lambda is any function, with mu, and then mu is not unique. Therefore, we have the choice of choosing the mu. However, this choice of mu up to this up to a given function of lambda, okay, doesn't affect our calculation of mu. Okay, similarly here, this is called this gauge condition. Okay, the gauge invariance of this electromagnetic theory. Similarly, for general relativity, we have we have this gauge transformation of the coordinate transformation. How we can easily understand that if I assume that x mu transforms as x mu minus of epsilon zeta mu, where zeta mu is very small and this is very infinitesimal small transformation that we are making, then h mu will look like h mu plus epsilon. This is Lie derivative of zeta eta mu. However, you can check that this type of transformation will leave the Riemann tensor invariant. Okay, so even with this transformation, coordinate transformation, which will change the h mu, but this Riemann tensor of the curvature in the space time will remain invariant. It will not change. Okay, so this is the gauge condition for gauge transformation for general theory of relativity. However, to fix the problem, what usually we do even in electromagnetic theory, we choose a particular gauge. So here we will choose also a particular gauge, which is also known as this harmonic gauge. What is this harmonic gauge? It is the condition that the dimension of this coordinate is 0. So if I express it in terms of g mu with this in the curvature and in terms of this explicit so partial derivative, I will get this term that which this condition gives rise to this zeta rho sigma gamma of lambda rho sigma equal to 0. You remember that in flat space, right, it's in Cartesian coordinates, in flat space and in Cartesian closure, this gammas are all 0. Okay, so means Cartesian coordinate is already a harmonic coordinate, so we do not need anything. However, even in flat space, you remember that the polar coordinates are not 0. In polar coordinates, all gammas are not 0. So in polar coordinates are not harmonic coordinates. However, Cartesian coordinates are in flat space. So this got its name from this type of gauge condition got its name from the fact that if f is a function which satisfies this type of equation, it is called a harmonic function. Okay, then f is called a harmonic function. So here this coordinate takes the role of a function, which here it takes, and so it's known as harmonic coordinate gauge or harmonic gauge. Okay, so and in the weak field limit, right, this condition can be written as in this form, del mu of h mu lambda minus half of del lambda h equal to 0, and this is called this gauge is known as this Lorentz gauge. This is explicitly written in terms of this perturbations, and this is called this Lorentz gauge, or even this is known as Einstein gauge, Hilbert gauge. We don't know how many more. It has many more name or not. So we still, but even with this gauge condition, we still have a gauge freedom. Okay, how? Because remember, we can change our coordinate by harmonic functions. This if I add some harmonic function here, it will remain same. This type of transformation this gauge will remain even satisfy that type of transformations. Okay, so that again one condition. Remember, there is also one freedom after the gauge freedom. Okay. However, let us proceed further and see in the harmonic gauge, the linearized Einstein equation, what they becomes, then they can be written in terms of this delambration of h mu nu minus eta mu nu delambration of h equal to 16 pi g. G is one somehow I don't, but it's 16 pi t mu nu. Okay, this you have to prove. This is also just straightforward to prove. Just try it. Okay, there is nothing new. And for the vacuum equation, you know this part will go away. This is 0. This will go to 0, and only this condition remains. And this is a very well-known equation. This is the relativistic wave equation. Okay, so we'll stop now. And hello students, welcome back. So we have derived the relativistic wave equation, which is the solution of linearized Einstein equation in vacuum. Okay, however, it is more convenient, you will understand when we proceed later, that is more convenient to work in the traced reverse perturbation. What is traced reverse perturbation? Traced reverse perturbation is denoted as h bar mu nu, which is nothing but it is equal to this h mu nu minus of half of eta mu nu of h. Okay, and you can guess that how it got its name, because h mu nu bar is nothing but the h mu nu bar, this trace of h mu nu bar is nothing but the negative of h, trace of h. So this, therefore it is it got its name as trace reverse. So in trace reverse perturbation, you see that harmonic gauge condition becomes much simpler. Del mu h mu nu h mu of lambda bar equal to 0. Okay, so this is the harmonic gauge condition. Okay, it has simplified even further, and the linearized field equation, the deambulation of h mu nu bar equal to 16 pi t mu nu. Okay, this also has become more convenient. However, the vacuum equations remain same. A deambulation of h mu nu bar equal to 0. Okay, so we will be solving these two equations. Okay, to see uh, how this gravitational waves or gravitational radiation propagates and what are the effects its effect. Okay, so in vacuum, so this is the condition. Okay, and we know how to solve this, right? This is relativistic wave equation. We know how to solve this. We assume some solution which is usually of this form. Okay, and then we take the real part of it, okay, to have this total entire solutions. So we assume that h mu nu bar equal to some constant c mu nu, which is also, you can see that this is a symmetric 0 to tensor, which is some constant. However, this is a tensor, symmetric 0 to tensor, and exponential I k rho x rho. Okay, and k rho you can identify with a wave vector. This is also a constant vector, but it's known as this wave vector. So we have a vector, we have a tensor in defining this solution of the Einstein equation in vacuum. Okay, and this perturbation is mu nu, this metric is given by this of this form. Okay, so if I now plug in the solution in this equation, if I plug this solution in this equation, what will I get is, you can easily check that this is nothing but the lambdation of that, which in terms of eta rho lambda and this eta rho sigma del rho sigma del sigma of h mu nu. So doing one after the other, you will have this k sigma minus of k sigma h bar of mu nu equal to 0, and you know that we have assumed that h mu nu is not always 0. H mu nu is the solution we are looking for. Therefore, the only thing that can be 0 is k sigma. So you see that this is the condition. This is a very known condition to us. This is the known as the condition for null. Okay, so this see, we find that this k rho, the wave vector, is null. So we can now say that this also is sometimes talked as that gravitational wave propagates at the speed of light. Okay, so this is the null condition, but more mathematically, this wave vector is null. Okay, and we know that this time-lag component of this wave vector is known as this frequency omega. Okay, we can therefore this total k wave vector can be written in terms of this frequency omega plus k1, k2, k3, which will be determined by for different problems it will be different. And the null condition, you can check, it becomes nothing but omega square equal to delta ij ki kj. Okay, this becomes the null condition. So let us now we have to find what is c mu nu and k rho and k sigma to find the solution of the Einstein equation or the gravitational wave solution. How the gravitational wave looks. To find that, we have to find out this coefficients. So this is a metric symmetric 0 to tensor. So we have it has 10 independent coefficient, and k rho has 4 components. Okay. However, with the null vector condition, we have one condition, which is the independent coefficient coefficients are 3. So we have 10 of this and 3 of this. Okay, we must find them to find out the solution of the Einstein equation of the gravitational wave. Okay, and what we do is finding them by eliminating the gauge and the coordinate freedom that we have. The gauge condition can be written in terms of this, like del mu of h mu nu bar equal to 0, which if I put it back this equation, right, it gives me this condition: I c mu nu k mu, right, e to the power exponential to the power k rho k sigma x sigma equal to 0, and this is not 0. Okay, and this can be 0 only if this is 0. So if c mu nu k mu equal to 0, it can be fulfilled. But this is a condition. This is a wave vector, and this is the constant coefficient. So wave vector is orthogonal to c mu nu. Okay, so this is not a one equation. Remember, there is mu where, so mu runs from 1 to 1 to 3, 0, 1 to 3. So we have 4 equations here. So number of, once we, with this condition, we can the number of independent coordinates c mu nu has now reduced from 10 to 6 because of these 4 equations, the independent coefficients of c mu nu. Okay, but we still have, this is only due to this gauge freedom. Okay, now we will use the coordinate freedom, which is x mu nu equal to x mu plus zeta mu, and in the harmonic coordinate, okay, delta x mu equal to 0, which transforms as delta of zeta mu equal to 0. So this is itself is a, you can see this is a wave equation, right? This harmonic condition, coordinate freedom of the harmonic condition gives a solution gives a wave equation of this form. So if I choose this zeta mu solution to be b mu nu e to the power I k rho k sigma x sigma, where b mu is the coefficient constant that we can choose. So we claim that this freedom, that means if I choosing b mu in a such a way, we will choose b mu in a such a way that we can convert the old coefficient c mu nu, that is c mu nu that has been defined till now, to a new set of c mu nu, and this new set, this old c mu nu doesn't satisfy the condition that I will be telling, but this new set does because of our freedom of choosing b mu nu. Okay, and if I choose b mu in such a way that this c mu of this new in the new chosen in the new form is equal to 0. Let us call this as equation C1, and also C0 nu, which is in the new coordinate, equal to 0. What is this equation says? Right, this equation says nothing but we can I can always have some 4 vector, and I can contract this 4 vector with the c mu nu, and to give a 0, okay, I can always align this 4 vector in such a way. However, I can choose this 4 vector to be in the time basis vector. Okay, and if I do that, then if I put this back here, we will get this equation. So this is nothing a new equation. This equation. This is the choice of b mu or the choice of 4 vector. Okay, so this depends on the choice of my 4 vector. So under this change, this type of new conditions, the perturbation, how the perturbation metric now looks like, let us see. N means new, O means old. So h mu nu n is nothing but old, h mu nu old minus of del mu zeta nu and del nu zeta mu. Okay, so and therefore this is the ordinary perturbation. The trace river perturbation now becomes h mu nu is h mu nu bar of nu is h mu nu. This is how it is defined, and if I put back this everything we know about h mu nu old, it becomes h mu nu bar of nu is h mu nu old minus del mu zeta mu minus of del nu zeta mu plus of eta mu nu delta lambda of zeta lambda. Okay, and implementing the solution from h mu nu, means if I put this h mu nu 0, or old was, remember, c mu nu exponential I k rho x rho, and zeta mu as b mu k rho x rho exponential I k rho x rho. If I put them back, I can have this coefficient, c coefficient, c mu nu in the new coefficient in terms of the old coefficient, plus in terms of b mu and b nu, okay, in terms of b's and the old c's. And now if I impose this c1 condition here, right, this gives me k lambda b lambda in terms of uh, c old mu mu, okay. And if I impose this condition c2, that means this condition, okay, because we now have understood how new is written in terms of old, I can implement that in the old one, and I will get how b0 will look like. b0 is nothing but I of twice k0 c00 half of c0 mu mu, okay. So I can write b0 in terms of this c00 and in terms of the old c's, and if this is for nu equal to 0 and for nu equal to 0, I can also write bj. J means this spatial part, okay, in terms of again this old c0 and the old c0s, okay, c mu news, okay. So I have got everything I want to have, okay. So b's are the chosen form of this we choose, okay. This I say that I have chosen in this way, that it gives me my the conditions, uh, these conditions are fulfilled, and that's how this condition was fulfilled is if I choose b0 of this form, okay, then this can be fulfilled. So this is how the gauge freedom and this coordinate freedom are used to eliminate different c mu nu. Okay, so the c1 condition is a one condition, that is uh, this is a single condition because it is the diagonal one, okay, and it is some single equation. However, c2 has four conditions, so we have five conditions in total. However, remember that the c2 for nu equal to 0 is nothing but this old one, that old condition that we got back, okay. You can check that. So this is the old condition that we got back. So this doesn't give me any new conditions. So our total conditions is c1 plus c2 is 4, okay. Now let us find out what are the independent c mu nu's. How many c mu nu we have to find out. So it has now it has only two independent continents, right, components, right. So therefore c and c mu nu is, if I write this nu as in terms of this, we just suppress this nu, we have two independent quantities that we have to find out for this wave, and this two independent coefficient of c mu nu gives the physical information characterizing the gravitational wave. However, we must remember that we are in this gauge, okay, this harmonic gauge and Lorentz gauge, okay. So in this gauge we only have two independent c mu nu to find out, okay. So welcome back, students. So how does the wave behave? We have found out how the solution will look like because we have got all this c mu nu's, but let us explicitly see how the wave behave, okay. So let us assume that this wave is traveling in the x3 direction. X3 means, let us say that it is the z direction, okay. Therefore this wave vector takes this form omega 0 0 k3. K3 means the wave vector corresponding to the z direction. But from this null condition, we can write this k mu nu also to be equal to omega 0 0 omega. Okay, if I know 1 omega, I also know this. From this null condition, I also know this the wave vector for this z direction. Okay, but we also have this orthogonal condition, k mu nu c mu nu equal to 0 and c 0 nu equal to 0. Therefore, if I put this back, mu, that means if I explicitly write in terms of temporal and spatial coordinates, and we know that this temporal part is 0, so we have this c3 nu or c the spatial nu equal to 0. Nu can be anything, right? 0, 1, 2, 3. So this is the condition that we get. However, you see that as with this and this condition, we only have this 4 non-zero components, right? C11, C12, C21, C22. But we know that C mu is a traceless and symmetric, right? So what we have is C11 equal to minus of C22. This we should have, unless it will not be traceless. And as it is symmetric, C21 is equal to C12. Therefore, the total C mu nu, this tensor will look like this. Okay, this is this 0, this is 0, and this is 0. Okay, only this there are four components which are not 0, but out of them only two are independent, that is C11 and C12. This can be written in this way, and you see that if it is the wave travel in the z direction, only this, let us say that this is x and this 2 is y. It is the x and y, the components of corresponding to cxy and cxx are non-zero, and only these two components specify how the wave will behave. Okay, all the nature of the wave is contained in this information, in these two C's. Okay, so using all the freedom, we have gone to a sub-gauge of the harmonic gauge. Okay, remember, and that is known as this transverse traceless gauge. Okay, gauge. So transverse traceless gauge. Why this is transverse traceless? This metric perturbation is traceless, right? Remember, C mu of was 0, and it is transverse. That means the wave is k mu c mu nu equal to 0. Okay, so this is known as this transverse traceless gauge. And in this gauge, you can easily check that this trace reversed metric perturbation is exactly equal to that of the of this original metric perturbations. So we can easily drop this bar part from it, and we have this h mu nu also has this solution with c mu nu. Okay, so it is easily, therefore we went to this traceless part. Okay, stress reversed solution h mu nu of metric perturbations. However, when we have got back the equations, and in this gauge we found that this is equivalent to this original metric perturbations, and therefore we can have the original perturbation without much difficulty. So what is the effect of gravitational wave? Effect means how a gravitational wave, if it is propagating in some direction, how it will affect the particles which is lying in its path. Okay, so in a transverse traceless gauge, okay, a single particle appears stationary to be in the first order in h mu nu. That means if we look at a single particle, and if a gravitational wave passes through it, but in the transverse traceless gauge we can always go back to in a coordinate system in which we will find that the particle is stationary. So the effect of gravitational wave cannot be understood if I look into a single particle. Okay, however, therefore what we should have is a measure coordinate independent effect. We should measure the coordinate independent effect for this if I want to have the effect of gravitational wave. So what we can do is we can have this relative motion of nearby particles. So to study a gravitational wave, what we have to see is how two particles move. If a gravitational wave passes through it, how the two particles move with respect to each other. So if I can study that, then I will have what is the effect of gravitational wave on particle or space-time. Okay, so to do that, let us assume that two nearby particles which have coordinates. This is the spatial coordinate. Okay, this is 0, 0, 0 and epsilon 0, 0. This is x1 or x direction which has some, and the gravitational which is along, that is x3 axis, that is z axis. Okay, then the proper distance between the two particles, we know that what is the proper distance. It is the distance, it is the mod of ds squared, and if I integrate it from 0 to this epsilon, and this will give us the proper distance between the two particles. So ds squared is nothing but this line element. We know how the line element can be written in terms of the metric. Okay, and this and it is only if we are looking only in the x direction, so we can easily factor out dx from it. Let us dx from it, and therefore this equation becomes simplified. It is gxs of half dx, and this can be written in terms of this is small Okay, this is effective small. We can write this to be of gxx mod of gxx half epsilon. Okay, only this is small, effective small, and doesn't depend on this. Let us say that it doesn't depend on x, so we can take this out, and we can integrate over dx over 0 to epsilon, which will give epsilon. Now this we know how gxx looks like, right? Because this is nothing but 1 of half, because this g, you remember g mu nu was eta mu nu plus half of plus h mu nu. Okay, so eta mu nu is 1 and h mu nu is, let us say that here we have only x component hsx. However, there is a half, so for small hsx this half transform here, so we will have 1 plus half of hxx. tt means we are, it's just to remember that we are in the stress transverse stressless gauge epsilon. You remember that hxx is not generally 0 because this is the metric, right? Metric perturbation that we are talking about, and it doesn't have to be 0. So we see that the proper distance, this L, which is not constant, it changes with time. Okay, and we know that how HSS is, right? The solution, it is a wave-like solution. So let us, if I assume that to be an oscillating wave, okay, it is oscillating, then we know that this proper distance between the two particles will oscillate. Okay, so this, because we have seen that this hxx has the oscillating solutions, because we have assumed that to be, and then we have seen that satisfied our conditions. So this is, if this is the solution is of oscillatory, that means hx is oscillatory, it increases, goes back to 0 and then increases. We will see that the distance between two particles first remains constant, then increases, then again go back to that form, and then again decreases, and again go back to the form and decreases. We will come to that more elaborately in the next section. Okay, how this will look like. Okay, before going to that direction, we will make one more remark, is that the distance between the two particles is proportional to the epsilon. Okay, which is, what is epsilon? You remember that epsilon is the initial separation. So gravitational wave create bigger distance change if the initial separation is bigger, and therefore you remember that gravitational wave detectors has to have huge arm length. Okay, to magnify that effect, because hxx is usually very small, because we are in a linear theory and this is very small, and we are very far away from it, so we have to have a maximum effect. This epsilon has to be greater. Okay, so that the gravitational wave detector can detect the waves. Okay, so next to I have what I have promised, let us go do that. So let us assume to see what are the polarization state of this gravitational wave. Let us assume a plane wave type of solution. Okay, what is the plane wave type of solution? That HAV is HAV of t minus x. Okay, so a wave traveling in the x direction with the speed of light. Okay, c equal to 1. So we know, and if it is traveling in the x direction, these two components are 0, only the non-zero components are h22 and h23. Okay, so these are only two non-zero components of h. Okay, let us first case 1, let us say that h23 is equal to 0, and what we have is known as h22 wave. So if I this is the metric element. Okay, t square can now be written in terms of, this is the eta mu nu, because h22 is 230, we will only have this g mu nu only have contribution from h mu nu. Okay, and epsilon means you can have epsilon, or if you want to don't have that, you can also put this to 0, but it's put this equal to 1. So we will have 1 minus h22 t of minus x and 1 plus h22 t of x. These are the, because these are only two non-zero components. Okay, and this line element will look like this. And if we are talking about two neighboring points, let us have this code, they have coordinate, let us say that y0 z0 and y0 plus dy and z0. Therefore the proper distance between them will be given by only this, right? 1 minus epsilon, again 1 minus h22. Epsilon is a parameter which says that this is small. Okay, you can have this parameter, or you can easily or else say that h22 is still small. If anything is fine. Okay, so now let us see what this tells us. And you remember that h22 has an oscillating solution, because we have an assumed plane wave, and we have know the solution of we have assumed the solution to be a plane wave solution, so this is an oscillatory solution. Okay, so what this tells us that at some time H22 is greater than 0, at some time it is equal to 0, and at some time it is H22 is less than 0. So for H22 greater than 0, right, H22 greater than 0, this becomes small, so particles move close to each other, and if H22 is less than 0, this is negative, so this is positive, so particles move apart. So okay, so this is uh, and let us go to do this, and if instead of uh, the neighboring points to be in terms of in y coordinates, let us have this neighboring points to be in the z coordinate, so we will have this exactly the this everything will remain same, only this will change because this remember h z z was having this positive quantity. So if this is the case, then ds the distance proper distance between neighboring points is like this. So this is the opposite of here. If h22 is greater than 0, particle moves apart, okay, and if h22 is less than 0, particle moves close. So let us see for h22 wave what happens. So let us, when there is no gravitational wave, these are the, let us say that this is the z axis and this is the y axis, okay, and these are the, in a circle, let us have the particles are there in a, like in a circle, and a wave which is coming in the perpendicular to this plane of paper, okay, and hitting the in the and the particles are in the yz plane, and the gravitational wave is traveling in the x direction, which is perpendicular to the plane of the paper. Okay, so if this happens, what we'll have is initially this y components particle will be move closer, okay, and z component, let us say the z component will move apart, okay, but as this is oscillator solution, first this happens, the h22 is greater than 0, for h22 greater than 0, this will move apart, okay, z components will move apart and y components will move close to each other. Then again h22, when h22 becomes 0, that again becomes a circle, and when h22 becomes less than 0, then what happens is z components come closer and y components become apart. So this is like a wave-like pattern, but a standing wave-like pattern. When a circle is forming an ellipse, and again a circle and an ellipse in the opposite direction. This is like having a this type of motion. Okay, um, this type of motion. This is an oscillatory plane gravitational wave is. Therefore, if an oscillatory plane gravitational wave is in the x direction is incident on a ring of particles situated in the yz plane, the ring is distorted in a pulsating wave. This means like this particles will be pulsating in form of an ellipse and a circle and ellipse continuously. So this is called the plus polarization. This is one of the polarization that we are talking about. Let us have another case. Okay, let us have, if the h22 is 0, what we'll have is h23 wave. So if I write the metric element, it will have this minus dt square, dx square, dy square. However, this dy dz will not be 0 because this is the component coming from this perturbation, and everything will be same as this flat metric. Okay, now if I what I do is I perform a rotation in the 45-degree in the yz plane. So that means now my y coordinate becomes y bar, which is nothing but 1 by root 2 of y plus z, and z becomes z bar, which is nothing but 1 by root 2 of minus y plus z. So if I put this in this equation, you can check very easily. You will get exactly the line element that we have got for the h22 wave. Okay, so this solution will be same, right? And this there will be the particle will be, if a gravitational wave traveling in the x direction hits a particle in the yz plane lying in the yz plane, it will behave like the previous one. However, there is only one difference comparing with the case 1. H23 will have the same effect as H22. However, with the axis rotated at 45-degree. So now let us see how this will be. Right, this is the particle when this is the particle in a circle. Okay, when no wave. Once the wave comes and hits this, if there is a H22 is greater than 0, now this is everything will be same, but this will be at an angle 45-degree. Okay, so this is an like a pulsating ellipse, but pulsating in the like a cross, right? X cross, like this, pulsating in this and this way, right? So this type of pulsation or polarization of this wave is known as exploration or cross polarization. Okay, so H22 wave correspond to a C plus, okay, this plus polarization, and H23 as cross polarization, and the two quantities measure two independent modes of linear polarization. Okay, so still if I have a normal wave, which means the superposition of the two polarization, and we usually have both components present. So this is this the now if I have all means usually we will not only have X and plus polarization, we will have a mixture of the two, and if it is so, then we will have a different kind of motion, but it will be something of pulsating form. Okay, so this is how a gravitational wave affects particle lying perpendicular to it. Okay, therefore it can. Welcome back. Now we'll study something about gravitational wave sources. Okay, so till now we have always done calculation for a linearized Einstein equation in a vacuum. That means we have only observed waves coming originating from somewhere, but and we have observed it to be in a vacuum. And how, from where this gravitational waves are emitted, we don't know. But however, we will change this here. Now we will have something how waves and gravitational wave radiations are emitted, and what are the form of the wave equation if they are just emitted from some sources. Okay, we will do that. So the linearized Einstein equation, which has a source, is of this form. This is the trace reversed metric perturbation. There is the elaboration of that, which is equal to 16 pi t mu nu. Okay, okay, there will be an half there, which makes it 16, a minus of 16 pi t mu nu. Okay, so such an equation, we know that such equations are solved using green functions technique, because we have learned that in our class of electromagnetic theory. Okay, so let us just recap a bit. Okay, general wave equation with source, like let us have this determination f t of x is equal to s t of x, where f t of say let's x is the radiative field and s t of x is the source. Okay, and the green function, which is given by g t x s t dash x dash, is the field which arises due to the delta function source. This source is a delta function. Okay, and this is the green function technique. It tells us what it tells us. It tells us how much the field is generated at the field point tx at this point per unit source. Okay, at the source point, where the source point is at t prime x prime. Okay, so I have this solution of the Green's function is written as deambulation of gtx, and then the delta function of t and x. Okay, and if the field which arises from actual source is given by integrating the green function against st2, and the field which arises from actual source is given by this integration of g with s. Okay, so as the field is got back from this integration of this type. This is a 4-dimensional integration, remember. Okay, for space time, 3 space and 1 time. Okay, so and we know many things about this green function operator. The green function for the wave operator is well known. Okay, this is a well known function, which is a delta function t prime minus of t mod of x minus x prime by c. This is over 4 pi x minus x prime, where this is this part is known as this retarded time. It gives the lag of associated with the propagation of information. This is comes from this causality. Means information travels with maximum at the speed of light. Okay, so this is a well-known form of this green function for the wave operator, solution of green function for the wave operator. Okay, so if I now use this technique in the linearized to solve the linearized Einstein equation, okay, and taking only the spatial part in the traceless transverse gauge. Okay, what we have is we can write this h mu nu bar in terms of h mu nu, which is a function of, let us say that tx. X is I am written here is not a one dimension, it can be 3 dimension. Okay, so it is 4g, g is, can be assumed to be 1, integration of 1 by x minus x prime t mu nu. This is the energy moment of pressure, which is the source which we are for here. T mu nu is the source, and this is integrated over this 3 spatial dimension. Okay, so what we have is, consider let us consider that the gravitational wave is generated from an isolated source, but which is very far away from us. Okay, before going there, before going to the isolated source and far away, remember the Fourier transform of some function phi t of x with respect to time alone. So Fourier transform of that is denoted by phi tilde of omega. Transform this Fourier transform of t is omega frequency. Omega is given by this 1 by root 2 integration of dt to the I omega t phi of tx, and phi of tx can also be written in terms of phi tilde with this form. Okay, now integration is over omega frequency. Okay, now if I remember this, therefore for the metric I can instead of writing in terms of t and x, I can write in terms of omega and x. Therefore I have this tilde part, okay, which is nothing but dt of e to I omega t h bar of mu nu t of x. And we know how this looks like. If I put it back here, h bar of, we know how it looks like because we have estimated with it. This is of this form. If I put it back here, okay, this and again tilde is t tilde is the Fourier transform of t mu nu tilde is Fourier transform of t mu nu. I can have this h mu nu tilde of this form. Okay, this is the three-dimensional. We are talking about the spatial dimension. Now let us put our condition for an isolated source which is very far away and slowly moving. So we can have, instead of x minus x prime, this x is x prime is very small. If I say that this can be integrated x, which is this is r. Okay, x minus x is nothing but this r radial. This is the source distance from us, and this elongation of the source is very small. Delta is very small. So if delta is very small and it is moving very slowly, then delta of r is very less than omega to the power minus 1. Okay, 1 over omega. So 1 over omega is its proportion t. Okay, so if that is the case, then this and this part can be written in terms of e to the I omega r over r. Okay, so this therefore this this test reverse of this h mu nu tilde is given by this form, which only have integration over this t mu nu tilde. Okay, and the harmonic gauge condition is takes this form, del mu nu h mu nu bar of tx. Okay, and if I put this tilde over here, right, it will even simplifies to h mu nu of 0 nu. Okay, it's 1 over omega del I h I nu. Okay, this you can just easily prove that. Try to prove this. Okay, this will test you something. You can understand something from it. So if, as I said, the space-like components are enough, so I can do this integration, and this integration, this is try proving this. This is an integration, interesting integration. This is a 4-5 line proof, but just try it. Okay, this integration is nothing but omega square x prime I x prime j t 0 0. Okay, so now tij can be written in terms of t 0 because we are talking about, remember, we are talking about only the spatial part. T mu has gone to t0, but tij can also be written in terms of t 0 0. So we will have our solution only in terms of t 0 0. So h mu nu can be written only in terms of t 0 0. What is t 0 0? Remember, t 0 0 is the energy density part. And usually in gravitational wave papers and all those people doing here, it's convention to define what is known as this quadruple moment tensor of the source qij, which is nothing but 3 times. Let us, instead of always writing x prime, let us change our coordinate to y. So in general coordinate, this is 3 of yi yj t00 t of y dqy. Okay, so this is the how the conventional quadruple tensor of defined. This is the quadruple tensor for the source of the energy density. Okay, therefore the Fourier transform of the quadruple momentum tensor, we need that because we are always dealing with the Fourier transform equations here. So which is of this form. So this gives this takes a very simple form, and then now this can be brought back to our original space. and tilde basis in the t and x in the t time and x part, and then we have this solution. Okay, and this is, you can see that this is nothing but 2 over 3 of r. R is the, r is the distance. Okay, d square, the second derivative with respect to time of this quadrupole moment, change in the quadrupole moment. Okay, this is the second derivative over the quadrupole moment. It is proportional to it, and it is done at t equal to tr, which is t minus r by c. Okay, so therefore the gravitational wave for an isolated non-electric object is proportional to the second derivative of the quadrupole moment of energy density. This relation you have always heard about when you are, because this is the era of gravitational wave and all those things. We have always heard about that this is proportional to the second derivative of this quadrupole moment. And if the second derivative of the quadrupole moment is non-zero, then and only then we have a uh, what is known as a gravitational wave. You have always heard about this, and now you can check that this is exactly the case. Okay, remark. What is the remark? Let us make a remark. So the electromagnetic radiation emerges from a dipole moment of charge density, right? You remember that the electromagnetic is from the dipole moment of radiation is caused due to the dipole moment of charge density. However, gravitational wave radiation emerges from the quadrupole moment of energy density. Okay, or sometimes it's known as also mass energy density, mass density, because C is suppressed. Okay, sometimes. And you know that usually in most cases quadrupole moment is less than the dipole moment. Therefore, gravitational wave is weaker than electromagnetic wave, and it took so many years to even discover gravitational wave. After say more than 100 years that we have got electromagnetic waves, we have to wait more than 100, no, 2 centuries maybe, to get gravitational wave detection. So let us check this from a star. So let us observe what is known as the radiation coming from a binary star. Okay, so what is a binary? Binary is a star of binary is a component, is a star component which is made from movement of uh, two stars. So they are in the gravitational effect of each other. Okay, so here what we do is we consider a binary. Okay, and this binary has some special thing. So this the binaries are due to two equal stars rotating around each other. So as their masses are same, you know that they will be rotating around their common center, which means this will be r and this will be also be r. Let us call this star A and this star B. Okay, so we will do some Newtonian approximation calculation. So if they are moving in a circular orbit, we can always equate the force due to the gravity with centrifugal force. And if I do that, so gmm by r square, that means gm by twice of r, because this is the distance between them, square equal to mv square by r, velocity. V is the velocity of this each star. Okay, and if they are moving in a circular orbit, their velocity is constant. Okay, so this we have assumed circular orbit to make our life easier. It can be even be done for a elliptic orbit. Okay, so the velocity can be given in terms of this gravitational constant, this mass, and the distance between them, and therefore the time period and the frequency omega can also be given in terms of their masses and the distance between them. So let us we can write down the position of each star as a function of time or function of frequency. Okay, as a function of time, and this is the position. Let us say that this is a circular motion, this is a planar motion. Okay, so they are moving in a plane, and let us say that they are moving in this x1 x2 plane, which is perpendicular to the x3 axis. Okay, and therefore this position, the coordinate of star A, that is denoted by x1a, is r cos omega t, and star B and this let us say y, this is x and this is y, so y is r sin omega t, and that of star B is r cos omega t and minus r sin omega t. Okay, if this is the case, okay, and then we can write the corresponding energy density T00, which is mass, that is, and which is given by this delta function. Okay, and delta function, you can check that with this type of delta function you can get that you will get back that if I put uh, x3 to be equal to x1, we will get the mass of the star A, and if I put it to be in B, we'll get back the mass of star B. This type of delta function, this is written in terms of delta function because we know how the green function works in a delta function technical way. Okay, so if I write the energy momentum tensor, the energy tensor in this way, I can find out this quadrupole moment. Okay, this it will have three non-zero components, q11, which is 6 m r square cos square omega t, which can be written in terms of 3 m r square 1 plus cos twice omega t. G22 is again, I think this will be 3 m r square 1 minus cos 2 omega t, and G1 equal to G21, which is 3 m r square sine of twice omega t. So therefore this Hij bar can be written in terms of this cos omega t and sine omega t, and maybe in terms of Tr. This Tr is the thing that we know, T minus R by C. Okay, so this is how this gravitational perturbation will look like. However, usually we don't before the measurement of gravitational wave measurement came up, now we can measure this perturbation, this thing. Okay, but before previous let me say just 5-10 years back, we were not able to do that. However, some measurement was done with gravitational wave calculation. So what is the measurement that was done for gravitational wave emitted from a pulsar was that they measured the energy emitted via the gravitational wave. Okay, how the energy emitted? The energy emitted, that means if these two stars are moving around in a binary, they're moving around each other, they are not constant. With time, this thing is they are inspiraling each other. Okay, and with time they are coming close to each other very slowly, using angular momentum and energy. They are coming towards each other, and this loss in the energy was calculated by someone. I will come to that. Okay, and that energy loss is the energy, that is what I talk about, what I denote by that energy emitted via gravitational wave. Okay, so however, to be precise, to do such calculation, linearized theory fails here, because to do such a calculation energy emitted by a gravitational wave, we have to do at least take up to second order terms in hv nu. Okay, so we cannot do with linear theory, we cannot calculate energy emitted by a gravitational wave source, because see that what we with t mu nu we have assumed for linear theory, we have assumed t mu nu to be doesn't depend on the h mu nu. However, to have energy emission, we should have this t mu nu to be function of time, that means to be and that should be proportional to how h mu nu the perturbation is. Okay, so we have to go to the at least one order higher in h mu nu, at least the second order in h mu nu. So if I do that, and if I do all the calculation, then I can say that the energy emitted, which is delta E, is written as over S some surface T0 mu eta mu del 2x del square x dt. Okay, and what is this is written only this T00, that means this temporal part that we have done just now, the temporal part over some surface zeta. Zeta is the surface of constant time. Okay, and T mu is the energy momentum tensor, but remember that this is the perturbation one along with the perturbation, not only the energy part, but also it has some perturbations, and therefore this is small t. And then you can do, if I do this, you can have a lengthy calculation, you can try some advanced book. Then you can have the delta E is proportional to the integration of power p dt, where p is the power, and which is given by the third derivative of qij. Okay, this is of this form in iterated time. Okay, and qij, this capital Qij is nothing but the test reversed of this quadrupole moment. Okay, so this is the test reverse part of the quadrupole moment. Qij is 1/3 delta ij delta k qij. So for binary star, if I do this for a binary star qij, I can do this calculation for a binary star qij, and you can find that qij is proportional to this, right? This is from this equation. This is from this equation. Okay, you can just put it back here and redefine qij. you will get this QIJ of this metric of this form. Now third derivative also is very easy to find because all this term will come out. Okay, 3 3 3, so 3 3 and then something. Okay, so this will come out. So we will have the third derivative of Qij will be 24 m r square omega q sine of n with this metric. And the total power is, if I now do this calculation of total power over time, the total power will be 2 by 5 m to the power 5 r to the power 5. This I think is right. If I change omega in terms of m and r and g, have here there are some terms of g. I have assumed g to be 1, therefore I have again missed that. So the total energy emitted is in terms of fifth power of mass and fifth power of radius. I have to check that. So this was calculated by Hulse and Taylor for a binary star PSR 1913 plus 16 in 1974, and that was the first proof of that gravitational wave, that is gravitational radiation is there, and this and the energy that this system is losing due to the gravitational wave. And for that calculation they was awarded Nobel Prize in 1993, I believe. Okay, and this is how binary star emits gravitational wave. However, for present calculation, for present days, this is enough. Okay, this we have been able to measure this perturbation Hij metric perturbations.